Welcome to the new era of video creation with BeoZ8. This is our new series on AI teaching natural language processing. Today, we will discuss the language modeling. Here are the contents. Language modeling is a core task in natural language processing, NLP, that involves predicting the probability distribution of a sequence of words. Simply put, it's about understanding language patterns, such as how likely one word is to follow another in a given context. Language models serve as the foundation for a range of NLP tasks, including speech recognition, machine translation, text generation, and spell correction. For example, in speech recognition, a language model helps the system to choose the most likely word from a set of possible candidates. In text generation, the model predicts the next word based on the context provided by previous words. At its core, a language model is trained to capture the statistical relationships between words and their context. There are several types of language models, each with different strengths and applications. N-gram models. These are statistical models that predict the probability of a word based on the previous N1 words. For example, in a bigram model, N2, the model predicts the next word based on the previous one. These models are simple, but often fail to capture long-range dependencies in text. Neural language models. These models use deep learning techniques to learn the representation of words in a continuous vector space. Unlike traditional n-gram models, they don't just count word occurrences, but learn to represent words in a way that captures their meanings and relationships. Recurrent neural networks, RNNs. RNNs are designed to process sequences of text, making them suitable for modeling the sequential nature of language. They maintain a hidden state that carries information about previous words, allowing them to capture dependencies over longer sequences. Transformer-based models. These models, including BERT and GPT, use self-attention mechanisms to process entire sequences simultaneously, capturing long-range dependencies and contextual relationships more effectively than RNNs. Transformers are the state-of-the-art models in language modeling. N-gram models are one of the simplest approaches to language modeling. In these models, the probability of a word occurring is conditioned on the previous N1 words. For example, in a bigram model, N2, the model calculates the probability of the next word given the previous word. One limitation of n-gram models is that they can only capture local dependencies, meaning they can't remember words or contexts that occurred much earlier in the sentence. To mitigate this, smoothing techniques, such as Laplace smoothing, are used to assign a small, non-zero probability to unseen word combinations. Despite their simplicity, n-gram models are still widely used in applications where computational resources are limited or the dataset is small. In contrast to n-gram models, neural language models use neural networks to learn dense, continuous representations of words, also known as word embeddings. These word embeddings capture semantic relationships between words. Similar words have similar embeddings, while words with different meanings are represented by more distant vectors in the embedding space. Neural language models are more flexible than n-grams and can capture complex patterns in language, such as synonyms, analogies, and polysemy, words with multiple meanings. They also generalize better to unseen words, as the embeddings can be shared across similar words. Common neural network architectures used for language modeling include feed-forward neural networks, FNNs, and multilayer perceptrons, MLPs. Recurrent neural networks, RNNs, were a significant advancement in language modeling. Unlike traditional models, RNNs process text sequentially, one word or token at a time. They maintain a hidden state that captures information about previous words in the sequence. This allows RNNs to model long-term dependencies and understand the context of earlier parts of the sentence when predicting the next word. However, RNNs also have their limitations. In long sequences, RNNs can suffer from the vanishing gradient problem, where gradients during training become very small, making it difficult for the model to learn from long-term dependencies. This issue was later addressed by more advanced models like long short-term memory, LSTM networks, and gated recurrent units, GRUs. To overcome the limitations of traditional RNNs, long short-term memory, LSTM networks were developed. LSTMs are designed to preserve long-term dependencies by using a set of gates that control the flow of information into, out of, and through the network. These gates include the input gate, which decides what new information to store, the forget gate, which determines what information to discard, and the output gate, which controls what information to pass to the next step. By using these gates, LSTMs can maintain and update the hidden state more effectively than vanilla RNNs, allowing them to capture long-range dependencies and sequences, making them ideal for tasks like speech recognition, machine translation, and text generation. The transformer model is one of the most revolutionary advancements in language modeling. Unlike RNNs and LSTMs, which process text sequentially, transformer models use self-attention mechanisms to process entire sequences simultaneously. This allows transformers to capture global dependencies, that is, the relationships between words that are far apart in a sequence. The self-attention mechanism enables the model to assign different weights to different words in the sequence, allowing it to focus on the most relevant parts of the input when making predictions. Transformer-based models like BERT, GPT, and T5 have set new benchmarks in NLP, including machine translation, text generation, and question answering. Word embeddings are a key component in modern language models. They are dense, continuous vector representations of words, which capture their semantic relationships. Words with similar meanings are placed near each other in the embedding space, allowing the model to leverage these relationships when processing text. Two widely used methods for learning word embeddings are Word2Vec and Glove. Word2Vec uses a neural network to learn embeddings by predicting surrounding words for a given target word, while Glove uses matrix factorization techniques on co-occurrence statistics. These embeddings serve as inputs to deeper models, like RNNs and transformers, providing rich, high-dimensional representations of words that help models understand language better. Language models are often used for text generation, where the model creates new text based on an initial prompt or context. GPT, Generative Pre-trained Transformer, is one of the most famous models for this task. Trained on vast amounts of text, GPT generates text by predicting the next word in a sequence, given the words that came before it. This allows GPT to produce coherent, human-like text. Applications of text generation include chatbots, creative writing, and summarization. However, generating coherent and contextually accurate text, especially for long passages, remains a challenge. For instance, the model may generate text that sounds fluent but lacks consistency with earlier content, or may lose focus on the original context. Pre-trained language models are trained on vast amounts of text data in an unsupervised manner, capturing general language patterns, structures, and relationships. These models, like BERT and GPT, are pre-trained on tasks like masked language modeling, BERT, or causal language modeling, GPT, learning rich contextual representations of language. After pre-training, these models can be fine-tuned for specific downstream tasks like question answering, sentiment analysis, or machine translation. Fine-tuning allows these pre-trained models to adapt to the specific nuances of the task, reducing the need for large labeled datasets for each individual application. When evaluating language models, one of the most commonly used metrics is perplexity. Perplexity measures how well the model predicts the next word in a sequence. Lower perplexity indicates better performance, as the model is better at predicting the correct word. For tasks like machine translation and text generation, other metrics like BLEU score are used, which compare the n-grams in the model's output to reference translations or texts. However, human evaluation remains the gold standard, as it considers factors like fluency, coherence, and relevance in ways that automated metrics cannot. Despite their successes, language models face several challenges. Data and computational requirements. Training large language models requires vast amounts of data and significant computational resources. Long-range dependencies. Models like RNNs and LSTMs struggle with capturing long-range dependencies in text, although transformers have improved this to some extent. Out-of-vocabulary words. Language models struggle with words not seen during training, making it difficult to handle rare or novel words. Ethical issues. Language models can inherit biases present in the data they are trained on, leading to biased or harmful outputs. Language models have a wide range of applications in NLP, machine translation. Models like Google Translate rely on language models to translate between languages. Speech recognition. Language models help convert spoken words into written text by predicting the most likely transcription. Text summarization. Language models can be used to create concise summaries of longer texts. Question answering. By modeling language context, these systems can answer questions based on a corpus of text. Looking ahead, language modeling is likely to continue evolving. Multilingual models. Future models will be capable of handling multiple languages simultaneously, improving their ability to process diverse linguistic data. World knowledge integration. Models may incorporate more world knowledge and reasoning capabilities to improve comprehension and response generation. Ethical improvements. More research is needed to address bias and fairness in language models, ensuring they do not perpetuate harmful stereotypes. Zero-shot learning. As models become more powerful, we can expect significant advances in zero-shot learning, where models can handle tasks without needing task-specific data. In conclusion, language modeling has been foundational to the success of NLP, with models like BERT, GPT, and T5 pushing the boundaries of what's possible in natural language understanding and generation. Despite significant progress, challenges such as data scarcity, bias, and handling long-range dependencies remain. The future holds exciting opportunities in multilingual models, zero-shot learning, and improving ethical considerations in AI systems.